Hey everyone, and welcome back to the channel. Today, we're diving into a topic that's all around us, every single day, from the ice in your drink to the steam from a kettle. We're talking about Chapter 3, Phase Equilibrium. It might sound complex, but I promise, by the end of this video, you'll see it in a whole new, much clearer light. So what exactly is phase equilibrium? Let's break it down. A phase is just a distinct form of matter, like solid, liquid, or gas. Think of an ice cube in a glass of water. You have the solid phase, the ice, and the liquid phase, the water, coexisting. Equilibrium is a state of balance. So, phase equilibrium is when different phases of a substance can exist together in a stable, balanced state without any net change. We see these changes, or phase transitions, all the time. When a solid turns directly into a gas, like dry ice, that's called sublimation. The opposite, when a gas turns directly into a solid, like frost forming on a cold window, is called deposition. When a gas turns into a liquid, like water droplets on a cold can, that's condensation. A liquid turning into a gas is vaporization. And the ones we all know, a solid turning to a liquid is melting, and a liquid turning to a solid is freezing. Each of these transitions happens at a specific transition temperature and transition pressure, which we can call TTRS and PTRS. For example, water melts at 0 degrees Celsius at standard atmospheric pressure. This is the point where both the solid and liquid phases can coexist in equilibrium. For this equilibrium to happen, a few conditions must be met. First, the system must be closed, meaning no matter can get in or out. Second, the temperature and pressure must be uniform throughout. And finally, the chemical potential, which is essentially the escaping tendency of a substance from a phase, must be the same for all phases present. If the chemical potential of the liquid is the same as the solid, neither one will dominate, and they'll exist in a happy balance. How do we visualize all of this? With something super useful called a phase diagram. A phase diagram is like a map. It shows you which phase, solid, liquid, or gas, is stable at any given combination of temperature and pressure. The lines on the diagram represent the conditions where two phases can coexist in equilibrium. On this map, there are a few very special locations. The first is the triple point. This is a unique point where all three phases, solid, liquid, and gas, coexist in perfect equilibrium. It happens at a very specific temperature and pressure, known as the triplet temperature, TTR, and triplet pressure, PTR. For water, this occurs at a chilly 0.01 degrees Celsius and a very low pressure. Another key location is the critical point. If you keep heating a liquid in a sealed container, its density decreases and the gas above it becomes denser. At the critical point, the distinction between liquid and gas disappears completely. They merge into a single phase called a supercritical fluid. This happens at the critical temperature, Tc, and critical pressure, Pc. Above this temperature, you can't liquefy the gas, no matter how much pressure you apply. The volume occupied by 1 mole of the substance at this point is the critical volume, Vc. To navigate these diagrams more precisely, scientists use the Gibbs phase rule. It's a simple but powerful equation. F equals C, P plus 2. Let us decode it. P is the number of phases present, like solid or liquid. C is the number of components, which are the chemically independent substances in the system. For pure water, C is 1. For a saltwater solution, C is 2, water and salt. And F is the degrees of freedom. This tells you how many variables, like temperature or pressure, you can change independently while still keeping the phases in equilibrium. Let's look at a single component phase diagram, using our good friend, water. The diagram has three main regions: solid, ice, liquid, water, and gas, steam. The line between solid and liquid shows the melting/freezing points at different pressures. The line between liquid and gas shows the boiling/condensation points. And the line between solid and gas shows the sublimation/deposition points. Notice the triple point where all three lines meet. Also, you'll see the liquid-gas line ends at the critical point. The negative slope of the solid-liquid line for water is unusual and explains why ice floats and why ice skating is possible. Now, what if we have two components? Let's take a mixture of nitrobenzene and water. These two liquids don't mix well. A two-component phase diagram gets a bit more complex, often including composition as a third variable. You'll see regions where the two liquids are immiscible, separate, and regions where they might form a single phase, depending on the temperature and their relative amounts. These diagrams are crucial in processes like distillation and extraction. Sometimes, a single substance can exist in more than one solid form. This phenomenon is called polymorphism. The classic example is carbon. Under different pressures and temperatures, it can form diamond, which is incredibly hard, or graphite, which is soft and used in pencils. They are chemically the same, pure carbon, but their atoms are arranged differently, giving them vastly different properties. The phase diagram for carbon shows us the exact conditions needed to turn humble graphite into a sparkling diamond. So why does all this matter? The applications are everywhere. In chemical engineering, phase diagrams are essential for designing separation processes like distillation and crystallization. In materials science, they help create alloys with specific properties. In geology, they help us understand rock and mineral formation deep within the earth. Even in the food industry, understanding the phase transitions of water and fats is key to making things like ice cream and chocolate with the perfect texture. From freeze-drying coffee to refining crude oil, phase equilibrium is the fundamental principle at work. So, to wrap it all up, phase equilibrium is the balanced coexistence of different states of matter. We can map these states using phase diagrams, which highlight key features like the triple point and critical point. The Gibbs phase rule helps us mathematically understand the conditions for this balance. Whether we're looking at a single substance like water, a mixture like nitrobenzene and water, or polymorphic forms like diamond and graphite, these concepts provide a powerful framework for understanding and manipulating the physical world around us. I hope this journey through phase equilibrium has been enlightening. It's a cornerstone of chemistry and physics that truly connects microscopic behavior to macroscopic properties we can see and use. If you found this video helpful, please give it a thumbs up, and don't forget to subscribe and hit that notification bell so you don't miss our next exploration. Thanks for watching, and see you in the next one.